So actually, like, yeah, pretty much the whole rest of the course is something, I mean, essentially extremal graph theory, although maybe some of the ideas from extremal set theory, the stuff we've been doing up to this point, some of those ideas are useful here, but yeah, the focus is going to be on graphs. What's a graph? Probably most of you know. But, I mean, in some sense, this is a graph is a set system, kind of. It's a set system of sets of size 2, right? So a graph, so I'll just kind of go through these things quickly. So G is a pair. VE, where V is a set of vertices. The singular is, of course, vertex. Although I feel like when I was new to graph theory, I would constantly like to say a vertex, because you say vertices, right? But anyway, so if you do that, it's fine. But does anyone else have that experience? Like calling, I've got 3 vertices or 1 vertex? Anyway. Anyway, so it's, yeah, vertices, vertex, and E is a set of pairs of vertices. So it's like a subset of V choose 2, right? Oh, and the elements are edges. So this is kind of formally how you could define a graph. I mean, but really, the point of a graph is, you know, I mean, the better way to think of a graph is just by drawing a picture, right? Draw some vertices. You know, so that's a vertex, right? If that's this is a vertex U and V. This is the edge UV. Where, I mean, technically, if I'm defining edges to be sets of size 2, you know, I guess kind of I'm saying that it's the set U comma V, but like we usually just write it this way, right? So just, you know, to save us from writing a bunch of curly brackets, let's just write an edge as UV or VU, right? So these are kind of, you know, because it's a set, it's unordered, so UV is the same as VU. It's, yeah. Occasionally we will want to like think about maybe other objects like directed graphs or hypergraphs, which are all very kind of closely related. But for now, let's just talk about graphs. Are these things familiar to people or? Okay. Also, one kind of weird thing in graph theory is like, you almost always kind of define the graph this way, like it's a pair VE, but then the whole time you never really say let G be the pair VE where V equals. I mean, we just say let G be a graph, and then, you know, VG is the vertex set of G. So where G is a graph, and then E of G is the edge set. So like usually we'll just say, let G be a graph, and then like, you know, we're not going to write G equal, like I guess you never really write down a graph this way, right? You don't write let G, and then to say what V is, say what E is. Like you just say let G be a graph, and then you start talking about V of G and E of G. Some special graphs that come up a lot. Complete graphs. Also called cliques. So these kind of are kind of used interchangeably in some sense. And that's, you know, So the notation is K1, K2, dot, 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 where, the number of vertices in Kn is n, and Kn has all the possible edges. So the edge set of Kn is all of the vertex set, choose 2. And here I'm just saying the vertex set has size n. I don't really care what you name the vertices. You could call them the numbers 1 up to n, but I'm just, yeah, it doesn't really matter. Cycle graphs. So you've got cycles, C3, C4, C5, etc., which is kind of, what you might think of as a cycle. You just put them in kind of a cyclic order and connect them up. So that would be a 5 cycle. And then if I take away one of those edges, I get a path. So path graphs, you've got, well, OK, I can actually have a path on one vertex. Actually, paths, the notation for paths becomes a bit controversial. Because there's a bit of a question, should P, let's say P3, should that be the path on 3 vertices or the path on 3 edges? I sort of was taught, from a young age that it's the path on, PK is the path on K vertices. That's what we're going to go with, although I'm starting to be converted. Like, I kind of feel like maybe it should be the path on K edges, but the course notes are written as vertices, so we're going to be like very vertex centric here. So yeah, Pn is the path on n vertices, even though in some cases it might be better for it to be edges. But so anyway, so P1 is like this, P2 is like this, P3, and so on. Actually, if we were to have a vote, like if I say P3, who feels like that should have 3 vertices, and who feels like it should have 3 edges? Oh, you're in, I guess, minority, but yeah, it's. I think maybe it should have 3 edges, but we're going with vertices. Oh, actually, I forgot to do something here. Oh, it's too late. OK, so there's so many kind of basic definitions to give you. Let's go through them quickly. So 2 graphs are isomorphic if they look exactly the same. So graphs G and H are isomorphic if there exists a bijection, let's say phi from the vertices of G to the vertices of H, such that UV is an edge of G if and only if phi of U, phi of V is an edge of H. And phi is called an isomorphism. And basically, we think of 2 isomorphic graphs as being basically the same graph, right? So if I take this 5 cycle labeled 1, 2, 3, 4, 5, and this cycle, this kind of star thing, right? These are actually, you know, formally they're different graphs. They have even different vertex sets, right? Like formally, the vertex set of this graph is not the same as this one. They're not the same graph, but for all intents and purposes, they're pretty much the same graph, right? So these are isomorphic. Because yeah, you just map 1 to A, 2 to C, 3 to E, 4 to B, 5 to D. Oh yeah, subgraph. So let's say H is a subgraph of G if I kind of, it's actually kind of hard to decide what's the best definition of this, but I'm going to just say that the vertex set just is a subset of H is a subset of the vertex set of G, and the edge set of H is a subset of the edge set of G. Although often when we think of this, we think of like, if I see a graph and I see a triangle in it, like we usually just say that, you know, K3 is a subgraph of that graph, but in some sense, it's kind of ignoring the label. But let's not dwell too much on these definitions. Well, let me introduce something I'm going to call a copy of a graph, and then this might be kind of useful. So, so a copy of H in G. So these are two graphs. Is a subgraph of G. That is isomorphic to H. So these are maybe things that you would guess maybe these words mean, but I guess here's a question. How many copies of P3 are there in, let's do an easy one, kind of, K3? Any guesses or thoughts under these definitions? Yeah? I think 3 is the way I would count this, like given how we've written things down. You know, if I take K3, there are 3 ways I can delete an edge. If I delete that edge, that gives me a graph whose vertex set is a subset of K3s because it's actually all the vertices of K3, and whose edge set is a subset of K3. So you know, the answer would be 3 here. Okay. Okay. So let's actually state an interesting problem now. So this is what we're going to focus on for the next, I guess the next couple of weeks or something. So here's an extremal problem. let H be a graph and n be a natural number. So, so the question is, what is the maximum number of edges in a graph with n vertices and no copies of H. Okay. So you've got a constraint, a sort of local constraint, right? It's like on any number of, let's say H has k vertices. Any k vertex set, you're not allowed to put the edges of a copy of H in there. And you want, subject to that, you want to have as many edges as possible. This number, so this actual maximum, so we let EX and H denote this maximum. So it is the maximum number of edges on an n vertex graph with no copy of H. And I guess what people usually, the terminology they use is they call this the extremal number of H. Or sometimes they call it a Theorem number, for reasons we're going to see tomorrow. So tomorrow we'll prove something called Theorem's theorem. Any questions about any of this so far? Okay. So the first thing we're going to prove is kind of the nicest kind of non-trivial case. I mean, there are some trivial cases here, right? If I say H is K2, how many edges can you have without having a copy of K2? None, right? Yeah. So that's kind of not worth proving, really. But the first kind of non-trivial case that comes up is, what about K3? What about triangles? Right? That's what K3 looks like. It's just a triangle. So what's the maximum number of edges in a triangle-free graph? So this is a theorem due to Mantel, or Mantel, I'm not sure, from a long time ago, 30s, 40s, I can't remember, which says that for any natural number n, the extremal number I guess you can also call this like the nth extremal number or something. But anyway, the extremal number of K3 is the floor of n squared over 4. So this is kind of a satisfying theorem, right? Because it actually gives you, it's an exact value. We're going to see when we kind of go to more kind of diverse sets of graphs, like if we go from, next time we're going to do general cliques. So if we'll change K3 to KK, we're also going to get a nice satisfying answer. But then we're going to change this to a general graph H, and it'll be a little bit more of an approximate answer, but yeah. But this is kind of a nice result. Okay, so I want to show this is equal, so I need a lower bound construction. And probably a lot of you have seen this before, but so one thing about triangles is that they can't show up in a bipartite graph. So bipartite just means, so I take a graph where I take, I put the vertices into two classes, and then I put all the edges between them. Well, this is something called a complete bipartite graph. Where bipartite refers to the fact that the vertices are in two classes, like this, and all the edges go between the classes. And complete refers to the fact that I actually put every single edge between the classes. Right. Are these concepts familiar, or if you do have any questions, stop me and ask. But yeah, and if you think about it, if I want to, so I'm going to take the construction I'm going to take is a complete bipartite graph. I want to have as many edges as possible. If you think about your kind of, go back to calculus when you were trying to figure out how to make a rectangle to, well, I mean, the number of edges is going to be the number of vertices in this side times the number of vertices in that side. The number of vertices adds up to n. It turns out if you want the product to be as big as possible, you want these numbers to be as close as possible. Unfortunately, though, not all numbers are divisible by 2. So anyway, the best we can do is you put floor of n over 2 on this side, ceiling of n over 2 on that side. And the number of edges will be floor of n over 2, ceiling n over 2. And there's no triangles. In other words, no copies of K3, because by pigeonhole, 2 of those vertices would have to be on the same side, and there's no edges. And if you do the math, this turns out to equal this value. So to show that this is equal to that, it's just a case analysis where you think, okay, what if n is even? Then both of these are just n over 2, so it's n squared over 4, which is just equal to, without the floor, it's just equal to that. If it's odd, it turns out you get n minus 1 over 2, n plus 1 over 2. You multiply these out, it gives you n squared minus 1 over 2, which turns out to be the floor of, anyway, over 4. In either case, you get this. Okay. Any questions about that? Okay. So let's prove the upper bound. So now let G have n vertices and no copy of K3. By the way, we should probably introduce some sort of a shorthand for this. So we can call this K3 free. So generally, let's say that a graph is H free if it doesn't have a copy of H. And yeah, we want to bound the number of edges. Okay, there's actually a lot of proofs of this. Actually, I've heard it joked before that no matter how you start, trying to prove this yourself, start in some direction. No matter which direction you choose, you can probably end up at a proof. Basically any idea that's reasonable will end up at a proof. So I'm going to give you one proof today, and then next time we're going to prove the more general Turan's theorem, where this is kk, and the proof is going to be totally different. I mean, so, and then probably later we're going to see even more things that imply this theorem that have different proofs. So this proof that I'm going to give today is based on just a bit of double counting and kind of convexity, like one of these convexity inequalities that we wrote down like a few weeks ago. But first, let's do the double counting. So, just we need a little bit of terminology. So a walk in a graph is a sequence of vertices, let's say v1, v2, up to, let's say, vk, where vi plus 1 is an edge for all I between 1 and k minus 1. And the length of this walk is confusingly, given the way that we've defined paths, the length of this walk, I mean, well, maybe it's not that confusing. Anyway. The length of this walk is k minus 1. It's the number of edges in the walk. So like here, there's no restriction. I'm not saying, like, you could use the same vertex again. Like, you could come back to the same vertex. You could use the same edge again, right? Your walk could just literally go like this, like back and forth on an edge. Then you could go over here. It could come back. It can do whatever it wants. It's just a walk. It's anything. But the only rule is that, consecutive vertices have to be adjacent. Okay. So what I want to do is count walks of length 2 in G. But I want to do it in two different ways, where somehow, by doing it in two different ways, I can extract some information about the number of edges in the graph. So for the first way of counting these walks, I need the concept of the degree of a vertex. So the degree of V is the number of edges that contain V. And the notation we're going to use d of v, unless at some point in the course I just randomly switch to deg of v. I don't know. I mean, both of these things are pretty common. So, okay. I want to count paths or walks of length 2, not paths, walks. So number of walks of length 2 in G. So yeah, there are multiple ways of counting this. Although what I would suggest is, like, actually probably the most natural way of counting it is, like, you might think I'll start at this vertex and I'll say how many choices are there for this one, then how many choices are there for this one. It's actually kind of hard to do that. Somehow it's kind of easier if I say I'm going to pick the middle vertex of the walk, and I'll say, given that choice, how many choices are there for the first vertex of the walk, and how many are there for the third vertex of the walk. So I'm going to sum over all V. So this is, I'm thinking of this vertex as being V. And how many choices are there for this vertex? the previous vertex on the walk? Yeah. And then now, so I'm going to have degree of v here. Now given, suppose I've already chosen these two, how many choices are there for this one? And this is, that was a bit of a trap. I thought someone would say degree of v minus 1, but technically it's degree of v actually, because of how I've defined walk. So a walk is not the same as a path, right? You're allowed in a walk to just do this. You know, you can go back to the same place twice. So by having chosen that one, it hasn't eliminated any choices for this one. This one could choose the same thing or a different neighbor of the vertex. Neighbor means a vertex that, yeah, where there's an edge, right? Is that clear or no? Yeah, this picture is misleading, right? A walk starting where the middle vertex is v, it could look like this. So there's kind of d of v times d of v minus 1 choices that actually look like that. But it could also look like this, where the first vertex is here, second vertex, third vertex. And for this one, there's d of v choices, because it's just choosing a neighbor. If you add these together, you actually get d of v squared. So the walk could look like this. So these are two types of walk. And so you could also think of it as there's this d of v choices for this, d of v choices for that, or you could think of it as if they're distinct, there's this many choices, and if they're not distinct, there's this many choices, and you add them up, and it makes d of v squared. Makes sense? Any questions about that? Okay. So this is something that comes up, it's going to come up a million times in this course. We have a sum of squares, and we want to bound that below by something that's more useful. Like, because in some sense, the sum of squares of degrees of vertices in the graph, I can't really directly use that to like estimate the number of edges. But you need to we need to kind of do something to it first. So I want to remind you about Holder's inequality that we at some point wrote down. Although this was a long time ago. So it says, so if I take x1 up to xn, y1 up to yn are any kind of real numbers, and p and q are bigger than 1, such that 1 over p plus 1 over q equals 1. It's kind of quite a strange condition in some sense. But then if I sum up I equals 1 to n of the absolute value of xi times yi, that should be at most the sum I equals 1 to n of absolute value of xi to the p, all raised to the 1 over p, times the same thing with y. So I equals 1 to n, absolute value of yi to the, well, okay, except with a q. So to the q to the 1 over q. This thing in particular is something it's also going to come up a lot, but the most, like, if you don't take anything else from this, the most important case of this for this course is thinking about what if we plug in p equals 1/2, q equals 1/2, and y1 equals ... up to yn, they all equal 1. Okay. So this is a thing that's always true, and we're going to sometimes need this in general. But let's think about 2. Yeah, these are upside down. P is 2, Q is 2. Yeah. Yeah, I knew it was one or the other. Does that make sense? So 1 over P is 1/2, and 1 over Q is 1/2, so they add up to 1, right? So in that case, so maybe I'll just write it over here. What you get is that the sum I equals 1 to n of absolute value of xi, because now yi is just 1, so it's just, that doesn't really, the yi is kind of gone, it just multiplies by 1. That's at most the sum I equals 1 to n. Absolute value of xi squared, but that's just xi squared. These are real numbers, so to the 1/2. And then we just sum up the number 1 over and over and over. We just get n. Which is the same as, if I kind of rearrange this, I'm going to try to get this by itself. So the sum of basically a sum of squares is always at least 1 over n. So where n is the number of terms in the sum, times the sum of the actual things. Technically, I could put, yeah, okay, I'll put the absolute value squared. But if you think about it, this is also at least, I don't really, if I took away the absolute values, it's still true. It actually only makes it smaller. So anyway, this thing is going to be used a lot in this course. So we've got a sum of squares. You can write it as 1 over n times the sum of the things without squares, and then square it. So if I apply this in this case, this is a sum of squares. So this is at least 1 over the number of terms in the sum, which is the number of vertices in the graph, times the sum of the degrees all squared. Okay, so I'm just applying this where my xi's are like the dv's instead. Is that clear? So you can think of your vertices labeled 1 up to n, where n is the number of vertices, and then this is the same kind of bound. Does anyone remember anything about the sum of the degrees in a graph? Something you might have learned in 222 or a graph theory course or something? Yeah, exactly. There's like this handshaking thing. Sum of the degrees, it's twice the number of edges. So this is exactly equal to 1 over the number of vertices times 2 times the number of edges, all squared. So it's like, 4 times number of edges squared over number of vertices. Okay, and this was kind of useful because it gives us something in terms of the number of edges, like, which is what we want to bound in the end, right? So this is a kind of counting the number of walks in one way, and we get a certain bound. Now I'm going to count the number of walks in a second way. And then we're going to put these bounds together and get the result. So number of walks of length 2 in G. I'm going to count it again. So this time, we're not going to, so last time we picked the central vertex and we asked how many choices are there for the other two. This time I'm going to do it in kind of a way that, actually, to me it seems a bit unusual, but what I'm going to do is I'm going to pick an edge. So kind of step 1, pick an edge. Step 2, decide which side, which vertex in the edge is the second vertex on the walk. So let's say the edge is UV. So it's either going to be U or it's going to be V. And 3, pick a neighbor. Neighbor just means something with an edge to adjacent to, or in other words, with an edge to that vertex. So pick a neighbor of that vertex. So this is going to count paths of, or walks of length 2, not paths, walks of length 2, right? Because pick an edge, and then I say, okay, either that one could be the second, like one of these, let's say, will be the first. Yeah, let's say one of them will be the first on the walk, one will be the second. So, and the one I don't choose is the second vertex, is the first vertex on the walk. So let's say I choose U to be the second vertex, and then I choose a neighbor, and that determines the third vertex. And that could be the same. I could choose V as the third vertex, right? You could choose the same thing twice. So if we count it this way, what we end up with is something like this. It's the sum over all the edges of G of the total number of choices for these last 2 steps. You might think I'm going to have a 2 in here by saying there's 2 choices for which one I choose as the second vertex, but I don't want to think of it that way. I want to think of it as, for the last 2 steps combined, there's D of U plus D of V choices. Because if I choose U to be the second vertex, I've got D of U choices, and if I choose V to be the second vertex, I've got D of V choices. In this whole proof so far, we haven't used that there's no triangles. So we need to do that at some point. And here's where it comes in. If I think about the choices for U and the choices for V, like if I think of their neighborhoods, like the things they're adjacent to, they're disjoint. Because there could not be a vertex, that is, so basically there's no vertex that's counted here and counted here, right? Because if it's a neighbor of both of them, that's where I get my triangle. So every vertex in the graph, can only be counted at most once by this sum. So this is at most the sum over all the edges of v of g, because u and v have no common neighbors. Is that clear? Or any questions about that? It can get a bit confusing because you have to also think about u and v themselves, but like v is counted exactly once, right? It's counted in the degree of u, and u is counted in the degree of v. These vertices aren't adjacent to themselves, so they're not counted twice either. So nothing's counted twice. Okay, and now I can just say, well, this is kind of an easy sum to compute, right? It's just the number of edges times the number of vertices. So what I've done is I've got an upper bound on the number of walks and a lower bound. And I just put those things together and hope that it's going to work. So the number of walks is at least 4 times the number of edges squared over the number of vertices. So number of walks of length 2. And it's at most the number of edges times the number of vertices. And now I just solve this for the number of edges. And I get this, which, so if G has n vertices, this is n squared over 4. And of course, the number of edges is an integer. So if it's at most n squared over 4, then it's at most the floor of n squared over 4. So, yeah. So because it's an integer, it's got to be at most the floor. Okay. Any questions about that? So yeah, a lot of things that we do will come down to, we've seen double counting a lot. Count things in 2 different ways, compare them, and sometimes magic happens and you get exactly the right bound. But yeah, this idea of, you're going to see a lot of times sums of squares are going to show up. And I guess this is an important thing to remember. This inequality, you have a sum of squares. It's at least 1 over the number of terms in the sum times the actual sum of the terms, all squared, right?